Hey everyone, Hihu here from LeetCode. Today we're solving LeetCode 392. Is subsequence. This is an easy problem. It comes under strings and 2 pointers in the LeetCode 75 study plan. At first glance, this problem looks very easy. We're just checking whether one string appears inside another. But don't let the easy tag fool you. This problem teaches a matching technique that shows up again and again in coding interviews. Once you understand the idea behind it, you'll be able to recognize the same pattern in many other string problems. So instead of just solving today's problem, let's understand the interview thinking behind it. First, let's understand exactly what the problem is asking. We're given 2 strings. The first string is called S. The second string is called T. Our task is to determine whether S is a subsequence of T. Now the obvious question is, what exactly is a subsequence? A subsequence is formed by deleting 0 or more characters from a string, without changing the order of the remaining characters. Notice something important. The characters do not have to be next to each other. They can have other characters between them, but their order can never change. That's the only rule. If every character of S appears inside T and appears in the same order, then the answer is true. Otherwise, the answer is false. Now this definition can sound a little confusing. So let's understand it visually using a few examples. Let's look at our first example. The string S is a BC, the string T is AHBGDC. Now let's try to match the characters one by one. The first character we're looking for is A. We immediately find it. Great. Now we don't need to look at anything before that position ever again. Our next target becomes B. We continue moving forward. Eventually we find B again. We move forward. Now we're looking for C. We keep scanning. Finally, we reach C. Every character of S was found. And more importantly, they were found in exactly the same order. So the answer is true. Now let's look at another example. The string S is a XC, a string T is still a HBGDC again. We successfully match A. Now our next target becomes X. We continue searching. We look at H, not a match. Then B, still not a match. Then G. Then D, finally, C. We've reached the end of the string. But we never found X. Since one required character is missing, the answer becomes false. Let's look at one final example. Suppose the string S is empty, and the string T is a BC. Is an empty string a subsequence? Yes. Because there are no characters to match. We've already matched everything. So the answer is true. These examples teach us 3 important things. First, characters must appear in the same order. Second, they do not need to be adjacent. And third, if even one required character cannot be found, the answer immediately becomes false. Now the next question is, how should we solve this problem? Let's ignore optimization for a moment. Suppose I ask you this question in an interview. What would be the first solution that comes to your mind? Most people would probably think like this. Start with the first character of S. Search for it inside T. Once we find it, start searching for the next character. Continue doing this until every character has been matched, or until we fail to find one. This idea is perfectly correct. It's simple, it's easy to understand, and it gives us the right answer. So let's first convert this thinking into code. Then we'll see if we can make it even better. Let's translate that idea into code. We start with a variable called current position. Initially, it points to the beginning of string T. Now we process every character of string S, one by one. For each character, we start searching inside string T, beginning from the current position. If we find a match, great. We update the current position to the next character in string T, because we've already matched everything before it. There's no reason to search those characters again. Now we move to the next character of string S. But what if we reach the end of string t, and the character is still not found? That means matching is impossible. So we immediately return false. If we successfully match every character of string s, then we simply return true. That's the complete brute force solution. It's straightforward. It follows exactly the way most people naturally think about the problem. Now let's verify it with a dry run. Let's use our first example. The string s is a BC, the string t is a HB, GDC initially. Our current position is at the beginning of string t. The first character we want is A. We start scanning. The very first character is A, perfect. We found our match. Now here's something important. Should we ever look at this character again? No. We've already matched it. So we move our current position to the next character. Now we're looking for B, we continue scanning. The next character is H, not a match. So we keep moving. Now we reach B, perfect. We've found our second match. Again, we move our current position one step ahead. Now we're looking for C. We continue scanning. We see G, not a match. Then D, still not. Finally, we reach C. That's our final match. We've successfully matched every character in string s. So we return true. Now let's test the second example. The string s is AXC, the string t is AHEBGDC. We match A immediately. Now we're looking for X. We continue scanning. We see H, not a match. Then B, still not. Then G, then D, then C. We've reached the end of the string. But we never found X. Once that happens, there's no point continuing. We already know the answer is false. So the brute force solution also works correctly. Now let's analyze the complexity. For every character in string s, we may scan through a portion of string t. Across the entire algorithm, every character of string t is visited at most once. So the total time complexity is O of n and m, where n is the length of string s, and m is the length of string t. Now let's talk about space. Did we create another string? No. Did we create another array? Again, no. We're only using a few variables to keep track of our current position. So the extra space required is O of 1. The complexity is already very good. But there's something interesting. This solution doesn't actually feel like brute force anymore. It already seems pretty efficient. Can we make the thinking behind it even simpler? Yes. And that's where the real interview insight comes in. Let's stop coding for a moment. Our solution already has excellent complexity. So what are we actually improving? We're improving the way we think about the problem. Let's go back to our first example. The string s is a BC, the string t is a HBGDC. We started by looking for a. Once we found it, did we ever need to search before that position again? No. Those characters are no longer useful. Now we only care about everything after that match. The same thing happens after finding B. We never go backwards. We only keep moving forward. That's the key observation. Both strings are always moving in the same direction. Neither pointer ever moves backwards. Once we realize that, a very common interview pattern appears. The two-pointer pattern. One pointer keeps track of our position in string s. The other pointer scans through string t. Let's call them pointer I and pointer j. Pointer I always points to the next character we want to match. Pointer j simply keeps scanning the larger string. Whenever the characters match, both pointers move forward. Because we've successfully matched one character. Whenever the characters don't match, only pointer j moves. Because we're still searching for the same character. Eventually, one of two things happens. Either pointer I reaches the end of string s. That means every character has been matched. Or pointer j reaches the end of string t first. That means matching is impossible. This is one of the most common matching patterns in interviews. Whenever one sequence has to be matched inside another, while preserving order. Think about using two pointers. Now let's implement this idea. The implementation is actually very small. We begin by creating two pointers. Pointer I starts at the beginning of string S. Pointer J starts at the beginning of string T. Now we continue while both pointers are inside their strings. At every step, we compare the two current characters. If they match, that means we've successfully matched one character from string S. So we move both pointers forward. If they don't match, we only move pointer J, because we're still searching for the same character in string S. Eventually, the loop finishes. Now we simply ask one final question. Did pointer I reach the end of string S? If yes, we matched every character. So we return true. Otherwise, some characters were never matched. So we return false. That's the complete solution. Notice how short the code is. The difficult part wasn't writing it. The difficult part was recognizing the pattern. Now let's watch both pointers move together, using a dry run. Let's walk through the same example one last time. The string S is a BAC, the string T is a HBGDC initially. Pointer I is pointing at it in strings. Pointer J is also pointing at it in string T. Now, let's compare the two characters. Do they match? Yes. That means we've successfully matched our first character. So both pointers move forward. Now pointer I is pointing at B. Pointer J is pointing at H. Let's compare them. Do they match? No. We're still looking for B, so should pointer I move? No. We're still searching for the same character. Only pointer J moves forward. Now pointer J reaches B. Let's compare again. Do they match? Yes. Perfect. We've matched another character. Both pointers move forward. Pointer I now points to C. Pointer J moves to G. Let's compare. Do they match? No, so only pointer J moves. Next, pointer J reaches D. Still no match. Only pointer J moves again. Finally, pointer J reaches C. Now both characters are the same. We've found our final match. So both pointers move one last time. Pointer I has now reached the end of string S. That means every required character was successfully matched. So the answer is true. Now think about the second example. The string S is a XC, we match A immediately. Now pointer I is looking for X. Pointer J continues scanning the remaining characters. It checks A, then B, then G, then D, finally C. None of them match X. Eventually, pointer J reaches the end of string T. But pointer I is still waiting for X. That means not every character was matched. So the answer is false. Notice how simple the algorithm becomes. One pointer keeps asking, what character do I need next? The other pointer keeps asking, can I find it? That's all the algorithm is doing. Let's analyze the complexity. Pointer I only moves forward. Pointer J also only moves forward. Neither pointer ever moves backwards. Each character is visited at most once. So the total time complexity is O of n and m, where n is the length of string S, and m is the length of string T. Now let's talk about space. We only used two integer pointers. No extra arrays, no extra strings. So the space complexity is O of 1. This is the best possible solution for this problem. Let's quickly recap. The key idea wasn't finding a faster algorithm. The key idea was recognizing a better way to think about the problem. Instead of repeatedly asking, where should I start searching? We simply let two pointers move together. One pointer tracks the current character in string S. The other scans through string T. Whenever the characters match, both pointers move. Otherwise, only the pointer in string T moves forward. That's the interview pattern to remember. Whenever a problem asks whether one sequence appears inside another, while preserving order, think about matching the two sequences using independent pointers. You'll see this same idea again in many string, greedy, and two-pointer interview problems. And that's how we solve LeetCode 392. Is Subsequence. If you found this explanation helpful, make sure to like the video and subscribe to LeetCode. Thanks for watching. This is Huu, signing off. Keep practicing. And I'll see you in the next one.